So our goal will be to prove the amazing extension theorem, which I stated at the end last time. But there's one more lemma that we need before we start the proof, and that's lemma 155. And I'm showing you part 1 here, and I'll show part 2 after we're done working with part 1. And the version in the textbook only has a part 1, but I'm also including a part 2, which you will see later. Okay, so we're in this very general setting in which the outer measure can be defined, which is a setting where you just have some collection of subsets of X that contains X and some non-negative function. No assumption about additivity or anything like that. Then this lemma tells you about the distance between the outer measures of two sets. So how different can the outer measures be between two sets? Well, no more different than the outer measure of their symmetric difference. So the distance between these two real numbers here, these two non-negative real numbers, is no more than the outer measure of the symmetric difference of the two sets. Okay, let's start by assuming the hypotheses. So there's all of our hypotheses. And next, observe this easy set theoretic fact that B is contained in this union of B prime with the symmetric difference between B and B prime. So you can do like an element chase or whatever, let X be in B and then prove that it's either in there or in there. Or a visual proof by cases. So this left-hand circle is B. The symmetric difference is this part shaded in green. Sorry, and the right-hand circle is B prime here. The part shaded in green is the symmetric difference. And then if I union that with B prime, then you get everything, right? So union the green and the blue, and you get everything. So I guess you could say we have it because we have this. So now we want to look at the outer measures of things. And we have proven a couple of useful facts about outer measure that just always hold for any subsets of X, anything in power set of X. Which is it's monotonic. So if B is a subset of something, then the outer measure of B is less than or equal to the outer measure of that thing. So this is from an earlier fact. And well, let me put a little reference for that since I've been numbering things. This was proposition 15L12. I think that was done on maybe the previous lecture or maybe the lecture before that. And then we also proved in the previous lecture, and it took a lot of work with double sums and stuff, just a lot of thinking about that, that mu star is countably additive. Although here we only need, countably subadditive, although here we only need finite subadditivity. So here we have this with this inequality. And that seems like one side of what we need to show, right? Trying to show this absolute value is bounded above by this number amounts to showing that this difference without the absolute value bars is bounded above by that number, and the negative of it is also, right? It's like showing plus minus this thing is bounded above. So if you subtract that to the other side, then that's one part of what we're trying to show. And the other part of what we're trying to show comes from applying this argument again, but with b and b prime flipped. So how about I just copy it? Erase these primes here, and stick a prime there. And that should do it. All right, and that's it for the lemma. So, oh, I should also include the reference for this. I guess this was lemma 154. We're currently proving lemma 155. So lemma 154 was countable subadditivity. Okay, there are the references. So, yeah, so it looks pretty easy, but of course this would have been probably challenging to prove if we tried to prove it right after we defined the outer measure, since we needed to use this finite subadditivity thing that we had to really think about before. Okay, one thing I want you to notice about this proof is that it really just relies on two facts about mu star. The fact that it's monotone, so we're able to go from this inclusion to this inequality. So that was provided by this proposition, the fact that it's monotone. And secondly, the fact that it's at least finitely subadditive. It was in fact more than that. But all we needed was monotone and finitely subadditive. And we were able to prove this. So now that we're here, I'd like to, without much extra effort, include a part 2 to this, which will put us in a situation where we are also looking at a function that is monotone and finitely subadditive. So let's say that A is actually an algebra of sets on X. So let A be an algebra of sets on X. And then let's assume that maybe it's confusing to call it mu again, but let me call it nu. How about? Let's say nu is a function and it's additive. So additive function on an algebra of sets. So now it's a kind of more special situation, more specialized situation. Then we need to be reasoning about things that we can actually apply nu to. So let's say these are actually in the algebra of sets. Then if I replace these with nus, like that, then this should hold. So let's be lazy and just edit the proof to work for this. Since I claim we also have for nu in this situation that it would be, since it's additive, it's finitely subadditive. If it's finitely additive, then it's finitely subadditive. And it's monotone. So then we also get this nice inequality. All right, let's see what needs to change. So let's assume A is an algebra of sets on X, and now nu is additive. And then same stuff, same observations, just down here. I'm going to replace these mu stars by nus. There we go. And these justifications now need to be updated. So, for example, why is it that nu B is less than or equal to nu, and then this thing that contains B is a subset? Well, earlier we proved that an additive function is automatically monotone. That was proposition 139, part 1, which I'm going to remind you about pretty soon, since we're going to use proposition 139 actually a lot. Let me update that here. Okay, and what about the finite subadditivity? Where does that come from? An additive function on an algebra of sets is automatically finitely subadditive. That comes from another part of proposition 139, part 2. There we go, and now we have proven the updated version of the lemma. Probably the better thing to remember than the actual lemma is the fact that anytime you have monotonicity, this property with subsets becoming less than or equal to, anytime you have monotonicity and finite subadditivity, you get this inequality. And for outer measure, you have monotonicity and finite subadditivity, even countable subadditivity, on arbitrary sets. For an additive function on an algebra of sets, you get those things, not for arbitrary sets, you cannot evaluate it at arbitrary sets, but you get it for those things in the algebra of sets.